So I'm excited to introduce Ron Rothblum, who's an associate professor at Technion and head of cryptography at Succinct. And he's going to tell us about some exciting and slightly concerning new attacks on deployed proof systems. Go ahead, Ron.
Thanks, Justin. Great to be back here. I'm usually in the business of proving security, but this talk is going to be about breaking security for a change, so hopefully it'll be interesting. So this is joint work with wonderful collaborators, Dmitry Kovatovich and Lev Sukhanov. So let's get right into it, and I'll try to explain what these things mean. So this talk is about the Fiat-Shamir transform. Fiat-Shamir transform is named after this beautiful paper by Amos Fiat and Adi Shamir from all the way back in 1986. Even though nowadays the way we view it is, I think, we've extended it quite a bit from what they originally envisioned. And in a nutshell, especially the way that it's interpreted nowadays, is that the Fiat-Shamir transform is just this amazing technique to take or transform interactive protocols and make them non-interactive, which is almost by magic. And it's really a critical component in most, not all, but most SNAR constructions. So it has become extremely important in practice. The original goal was a little bit different, but let's sort of focus on the modern interpretation of Fiat-Shamir. So to give context and kind of like see that we're all on the same page, our starting point is this notion of an interactive argument system. So we have a prover and a verifier. The prover is trying to convince the verifier that a statement X is true. What does that mean? So we have a fixed, say, circuit or computation that we care about C. And what we want to show is that there exists some witness W so that C of XW is equal to Y. So there's some sort of non-deterministic computation, and we want to verify that it's correct. The verifier knows X, the prover knows X, and the witness, both of them know the circuit C. They interact back and forth, and in the end, the verifier should be convinced. What does that mean? So if the statement is true, the verifier should accept. If the statement is false, no matter what a cheating prover can do within a reasonable amount of time, with high probability, our verifier is going to reject. So that's sort of our setting in the interactive world. Oh, and something that's going to come up in the talk is we're going to be focusing on public coin protocols, which means that the verifier messages are just random coin tosses. So they're not sort of like intelligent challenges, just random coins. And luckily enough, almost all the protocols that we actually care about have this form. And this is going to be important later on. So that's public coin. Cool, so that's an interactive protocol. And in practice, we kind of are, okay, nice to have an interactive protocol, but would it be even nicer to have a non-interactive one? And it's not just about, saving, less rounds and so on. Non-interactive protocols have the distinctive feature that you can post them somewhere and anyone can come along and verify, for example, on a blockchain. Okay, so it's really an extremely important feature. So what is Fiat-Shamir? Again, take an interactive protocol, make it non-interactive, and do it in a very generic way. So how does it work? What's the magic? Well, we start off with our interactive protocol. We have P talking to V. I'll denote the prover messages by alpha, and the verifier challenges, which we recall are just random coins by beta. And we transform it as follows. So we have a new proof system, PFS, VFS. To do it, we're going to be using a hash function, H. And I assume you are probably all familiar with this, so it won't be too slow. But the way it works is as follows. So you start emulating the proof system, right? So the prover can, generate and send over alpha 1, but now it can no longer wait to get the response beta 1. So rather than doing that, we still want it to be sort of unpredictable. So we'll compute beta 1 by hashing kind of everything we know, which would be like X and Y, and especially alpha 1 to derive beta 1. Now that we know beta 1, the verifiers are going to do it later on her side as well. But as a prover, we can keep going, right? So we can now generate alpha 2, send that in the same message, compute beta 2, and so on and so forth. By sort of replacing the verifier by a hash function, we can compute all the verifier challenges. So the transformation, to those who haven't seen it before, is it clear? And also to those who have seen it before. Right, so this is the suggested transformation. One thing I want to really emphasize is that while it is very, very simple as described, it is sort of notorious for implementation bugs. So this is a list, including one very recently, I think, on the Solana blockchain, which I think was made some news. And the reason is sort of while it's very easy to describe this way, in practice you have a very complex protocol and you need to make sure that you're really hashing everything possible that the verifier knows, that you can. And it's very easy to miss, so there have been a lot of implementation bugs. This talk is going to be not about an implementation bug, but really about using Fiat-Shamir sort of as you're supposed to. Okay, we can talk more about this.
So the implementation bugs are usually leaving out some of either X or the alphas?
Yeah, so the classical implementation bug is forgetting to include X, which means that a cheating prover could, like, based on, now that it knows beta 1, it can choose a good X for which beta 1 is easy. So kind of anything that the prover can potentially control, you have to include in the hash. And people know this by now, but they still, these mistakes come up all over. I should say that there is some nice work by Mikhail Oro, I think, on trying to standardize Fiat-Shamir and have like libraries so people make less mistakes. Cool, so we have this Fiat-Shamir transform. It's been extremely influential, incredibly important in cryptography. And to highlight some reasons, first of all, it's incredibly powerful just because interactive protocols are amazingly powerful. It's kind of like surprising how much interaction buys us. So stuff like SumCheck, GKR, the Fry protocol, a lot of the protocols that we really love and have designed are naturally interactive, and they really get a lot from this interaction. And all of a sudden, we have this, best of both worlds that we can enjoy, all of these benefits of interaction without actually interacting. So it's really, really powerful. It is highly practical and really like deployed everywhere. And a large reason for that is that it's very small overhead, right? All you need to do is like there's a hash function, very lightweight, no public key crypto, and so on. So it's very lightweight, so people like it a lot. And you can get, this goes back to being powerful, you can get a lot of mileage out of it. So starting off, in the beginning with efficient signatures, which was designed for, going on in theory land to things like CS proofs, and nowadays snarks, starks, all of that stuff. So we kind of really like the Fiat-Shamir transform. The question that we want to sort of like focus on in this talk is it sound? So first and foremost, let's start with the intuition. Why would you expect it to be sound? Well, we have the interactive protocol, which we're assuming is sound. And what makes the interactive protocol sound is when the prover generates a message, he doesn't know what the verifier's next coin toss is going to be. And that is crucial to the soundness argument in the interactive land. And it seems that when you do hashing, you have something similar, right? From a cheating prover's perspective, until he decides what his message is, he doesn't know what the hash of this message is going to be. Sort of makes sense, right? And therefore, it seems that it really mimics the interactive setting. So that's sort of the intuition. But as cryptographers, we don't love just settling for intuition. And indeed, for a long time now, we've had this analysis that we very strongly rely on, which is what's known as the random oracle analysis, which says, our hash functions are amazing. They're really, really good. They're so good that they are, they're so nonsensical, have no structure, that we may as well just treat them as totally random functions. So that is sort of like a leap of faith that is made, or a modeling assumption. And if you analyze your hash function as a fully random function, then it's been shown that the Fiat-Shamir works. You have to be a little bit careful, but you can make it so that it works. And now, with this in mind, the common interpretation has been, our hash functions are so good, we have security when the hash function is really good. So if we have an attack on Fiat-Shamir, it has to be because the hash function is not as good as a random oracle. It has some defect, and we should replace it with a different hash function. So far, so good? So that has been sort of the common wisdom for a while. And it's been the common wisdom despite the following amazing paper called The Random Oracle Methodology Revisited, which is from a good 20 years ago. It's by Canetti, Goldreich, and Halevi, who showed that there actually exist specific cryptographic schemes that are secure when using the random oracle model. So they're in the random oracle model. But in these schemes, if you instantiate the random oracle, no matter in what way, security is broken. So it's not the fault of the hash function. So you could use, no matter what hash function you use here, it's broken. Yes?
So specifically, what cryptographic primitive did this previous paper show?
I think they did a bunch of different things. I don't remember off the top of my head. I think they had encryption, maybe signatures. They couldn't quite do Fiat-Shamir, which is what I'm coming up to.
Are any of the attacks actually relevant in practice in this paper?
Good. So this has been on for a while now. I might ask, how are people still relying on the random oracle model and so on, given this attack? And the point really is that the schemes that were constructed here were highly contrived. So it's not maybe clear what I mean by contrived, but it is clear that they were specifically designed in order to fail. Okay, it's very clear when you look at them, they have a weird component that you would not expect to see that was intentionally put there. So it doesn't ruin security when you're in the random oracle model, but it ruins security when you instantiate it. Okay, and that is why I think the common wisdom remained and people were not really worried about the random oracle model. That answer the question? Yeah. So a couple of years after that, this is like journal versions, that's why the years are mixed up. But
so that was like a trapdoor trick kind of
yes,
thing in there? Okay.
In a sense. So there was an intentional trapdoor, if you like, meant in order to violate security when you instantiate the random oracle. A couple of years after that, the years are just like journal versions. So Barak and really like Goldwasser and Kalai struck the point. So they showed an example of an interactive protocol in the random oracle model. So sorry, it's an interactive protocol. It's secure. If you apply Fiat-Shamir to it in the random oracle model, by the previous result, everything is fine. But if you instantiate the random oracle, it's broken. Okay, so this is showing that Fiat-Shamir is insecure. You might start wondering, okay, are we in trouble? But again, here the interactive protocol that you start off with was contrived. And throughout this talk, when I say contrived, I mean it is very clear that it was intentionally designed to fail.
So these results, they're like constructive, like it's.
Yeah, it's an explicit protocol, and we're going to see something along this very soon. Yeah.
So basically, there's an explicit attack given. And
yes. So it's an explicit protocol and a fully explicit attack. More recently, in joint work with my student Ron Rothblum and Bertusek, Justin Holmgren, and Fermi Ma, we showed that actually, if you look specifically at the way that a lot of basically how hash-based snarks are constructed, namely take something like a PCP or IOP and compile it with a vector commitment. We showed that even for that type of construction, we have an attack, which seems more concerning, and I think it is. However, still we had a contrived component. So we had sort of two results here. One had a contrived IOP. So the underlying, I don't know if people are familiar, but a key underlying component of snarks is something called an IOP. We had a specific IOP for which the general methodology fails. That was one result, and the other result had a specific hash function for a Merkle tree or vector commitment that would make it fail. But again, we had a contrived component, so I don't think people were particularly worried about these attacks.
So the point here was just at least the high-level structure matched the practical construction.
Yes. So like it was getting more and more closer to actual protocols, and the contrived component was becoming less smaller. Yeah. And really, the point of this new work is that we show something that I would say is not contrived because it's a protocol that people have written a bunch of papers on doing it, and there are companies that are running it, and for which these papers show that it's secure interactively, but we show an attack when you compile using Fiat-Shamir. And by an attack, I mean that we can actually convince, it's fully explicit to Elaine's question, we can convince the verifier to accept a statement that is blatantly false, and we're going to see it. The order of quantifiers here is a little bit nuanced, so we're going to, I'll write a more or less formal theorem statement soon. So before showing you our actual attack, I want to start off with a motivating example, which is sort of in the flavor of the previous contrived protocols, just to give a sense of like what might go wrong. And I think it's cute, so let's do that. So it's a protocol. We have a prover and a verifier. And you're trying to prove something, I don't know, C of x is equal to y, not super important. And the protocol is going to look as follows. So the prover sends to the verifier a message M, okay? So far, so good. The verifier tosses a bunch of random coins. Think of lambda as a security parameter, so maybe 128 bits, okay? Random vector, sends that over to the prover. So far, great protocols. All protocols look like this. Now comes the weird part. So here's what the verifier is going to do. It's weird. The verifier takes the message M, interprets it as code in, I don't know, Rust. Do you like Rust? Whatever you like. C++. C++. To interpret it as a C++ program and starts running it. And it runs it on a specific input. So it feeds as an input to the program the input x, the claimed output y, and the code of M itself. Why does it do that? Because I want it to. It's weird. Okay? But does this sort of like thing remind anyone of anything from undergrad? Diagonalization, right? You're running the program on itself as input. So it's weird. Let's see why we're doing that. So not only, so we do this thing, M, so think of like this M of M kind of thing, and we check whether the result is equal to R. Now, what's the probability of that? Very, very, very small, right? Because M was determined before R was chosen. So this, on the right-hand side, is a fixed string, and we're asking what is the probability that a fixed string is equal to a random string. So why are we doing this? We'll see, but we're doing this. So if it happens to be this very unlikely event happens, we immediately accept. And if not, then you run your other proof system. You run Jolt, which is secure. So that's the protocol. And first, I want to say, yeah, this is Jolt. I want to claim that this is a secure interactive protocol. And the reason we already sort of sketched, right? The probability of this equality being true is negligible. It's exponentially small. So we can more or less ignore it. And we're just running some other protocol. And Jolt is secure, so everyone is happy. Right? So as an interactive protocol, it's secure. Let's think what happens when you apply Fiat-Shamir. So what did Fiat-Shamir tell us to do? So we're using some hash function h. And rather than choosing R at random, we are computing R by hashing whatever we know, which in our case is x and y and m. Okay, so R is computed as a hash of x, y, and m. And now for a prover to cheat in this protocol, what it needs to do is to find the message m so that R, which is just this thing, is equal to the right-hand side thing, which is this thing. Can anyone think of a message m that will make this equation pass? H, right? So if you send H, it passes. You can make the verifier accept any statement with probability 1. So it's fully explicit to Elaine's question. Fully explicit, and you can convince of any statement that you want with probability 1. OK, so this protocol is really contrived, right? You stare at this, and you don't expect to be running, like a user-specified message, treating it as a program, running it on itself as an input. No protocol would ever do something like this, right? So it turns out that our protocols are now sufficiently general purpose that in some sense you can do this. Okay, and that's what I want to show you in that talk today. So let's jump right into it and show that attack. So to describe the protocol that we're attacking, I need to give you a little bit of background. So basically 2 things. One is what is a PCS, or polynomial commitment scheme. And the second thing is the GKR protocol, or just like a little bit of information that you need about this protocol. So first of all, what is a PCS, or polynomial commitment scheme? So first of all, it's a really important component in most SNARK constructions. So it's a way to commit to a very large polynomial. And you have different variants, whether it's univariate, multivariate, multilinear, and so on. But you want to commit to a very large polynomial in a very succinct way, so that later on you can prove statements like p of x is equal to y. So I commit to a very large polynomial p using a very short hash, but later on I can prove to you evaluations. One of the luxuries of breaking security is you don't have to sort of define security of the internal things because you're breaking the overall thing. So I won't define formally what it means, but intuitively it makes sense. Cool. And specifically for today, we're going to be focusing on polynomial commitment schemes for multilinear polynomials over a finite field, or sufficiently large finite field. So that's one component we need. The second component is the GKR protocol by Guy and Shafi, or I should say Shafi and Yael and Guy from almost 20 years ago. So the GKR protocol is a statistically sound interactive protocol for proving correctness of a bounded depth arithmetic computation. So think of, I want to prove that C of x is equal to y, where C is some bounded depth arithmetic circuit over the field. Something worth emphasizing, because we'll change it in a bit, that this really deals with a deterministic computation. In contrast to what we were saying before, we want to prove that there exists, witness, blah, blah, blah. Here it's fully deterministic. There's a fixed circuit C. There's an input x that prover and verifier know. And we're proving correctness, C of x is equal to y. So I want to show you how the protocol works. We won't need too much details, but we'll need a little bit. So remember we said we're dealing with an arithmetic circuit. I drew it here from input layer at the bottom going up. And the circuit has addition and multiplication gates. And the way that you compute is you put in an input and you feed it into gates. You evaluate the gate and you move on, and then draw all the edges, but you go, you should think of it as a layered circuit, and you go layer by layer until eventually you evaluate the output. Okay, so this is just an evaluation of an arithmetic circuit. And now we want, let's say I'm an honest guy, of course, I am. So despite breaking some stuff today, when we feed in an input x, that determines the output y of the circuit. How does the GKR protocol work? Well, I'm coming along and telling you, hey guys, the output, this is X. If you evaluate the circuit, the output is Y. And the goal of the protocol is to avoid you having to reevaluate the circuit. So we want a more efficient procedure. So the first thing you do as verifiers is to choose, so we're going to look at a particular encoding of the evaluation of the circuit, right? So when we evaluated the circuit, for every layer, we got the values that we got during the evaluation. And for every layer separately, I'm going to look at an encoding of these values using a specific error-correcting code, which is the multilinear extension. In other words, I'm interpolating these values as a multilinear polynomial. The specifics don't matter that much for the talk. At one point they will, but it's not going to be huge. OK, so that's what I mean with the yellow bars here. So they're the encodings of the individual layers. So I come along and tell you, the output layer is supposed to be an encoding of this string y. What you're going to do as a verifier, first thing is choose a random point in this encoding and compute the value that is supposed to be there. So the entire encoding is very large, but you as a verifier, if you're only interested in one specific point, you can do this very efficiently. Why do you do this? Because intuitively, if I was lying, if the output of the circuit was not y, it was some other y prime, I take these two strings and I evaluate them at a random point. Because of sort of this error-correcting property, with good probability, the results should be different. OK, so now I've managed to reduce the claim about the entire output layer to a claim about a single point in this topmost layer, in the encoding of the topmost layer. So far, make sense? Cool. So that is the main part that we'll care about. But just to not leave you hanging, let's see how the protocol works from here on. So the next thing that happens is some little interactive protocol that manages to reduce a claim about the output layer, a single point in the output layer, to a single point about one layer below that. So there's a specific interactive reduction that manages to do that. It relies on the sum-check protocol, but the specifics won't matter for us so much. So I've managed to go from a claim about the red dot here to a claim about the red dot there, but then I could do this again and get a claim over here, and a claim over there, and eventually a claim over there after I do this for these steps. And the claim that I get about the input layer, I as a verifier know the entire input, so I can verify it myself. OK, so that is a structure, as the original GKR protocol. The way that GKR is used nowadays is a little bit different than how it was originally proposed. So I want to show you how we extend GKR in a sense. So as I was saying before, GKR was designed for deterministic computations. But nowadays, the way that it is used is also to handle non-deterministic computation. So I want to prove to you not only that C of x is equal to y, but rather that I know some secret, maybe w, so that C of xw is equal to y. And the way I will do this is by combining GKR with a multilinear PCS, and I want to show you how to do it. So here's the idea. So we have our prover and verifier. First thing that's going to happen is for us to sort of agree on what circuit we're using. So maybe first of all, the verifier will specify parameterization of the PCS. Okay, so in case our PCS usually will involve some sort of parameterization, so the verifier specifies it. And now the prover tells the verifier what circuit are we going to be dealing with today. Now you might think in practice the verifier is the one choosing the circuit for which we're proving stuff, but really we want, especially with soundness in mind, we want things to be secure even against maybe an adversarially chosen circuit. So I think of it as the prover choosing the circuit. Cool, so the prover has chosen the circuit. If I want my verifier eventually to be sublinear in the circuit. So what will happen now, and this I think of it as a pre-processing step, is that I'll only save just a little bit of information about the circuit C, which will be enough for my proof system. So rather than saving the entire circuit C, which is very large, the verifier at this point just saves a small digest of C, which I will denote by bracket C. So think of it as some sort of hash of the circuit description. Okay? And it's very short, much shorter than the circuit. So notice that this doesn't depend on the actual input X or the witness W. So we've done that. And now we want to start the actual proving. So now the prover gets the input statement X and the witness W, and the verifier gets X. What do we do? Well, first of all, I, as an honest prover, will evaluate the circuit. I get the result Y, and that's my claim. My claim is that the output of the circuit is Y. And I'll also compute a PCS hash of W, right? So I take W, I view it as sort of the guts of a multilinear polynomial, and I commit to it, so that later I can prove make evaluation proofs about W. What do I send to the verifier? I send the input claim X, I send the claimed output, which is Y, and I send this alpha, which is the PCS hash of W. It's very short, just a hash of the witness. So I send this over to the verifier, and at this point I want to think of, given X and W, there was a circuit that I want to evaluate, and I want to start running GKR with respect to that circuit. So let's recall how the protocol worked. We had the circuit, we evaluated it, and now we first thing that we did, you remember what that was? To look at the output layer and compute the multilinear extension at a random point, right? So that's what we're going to do. So verifier chooses a random point in the multilinear extension, which I'm denoting here by y hat of y. So whenever I put a hat, it interpolate this data as a multilinear polynomial and evaluate it at R. I send R back to the prover, and now the prover and verifier start engaging in the GKR protocol. So reducing it layer by layer until eventually we get a claim about the input, right? But notice that the input here is not just X, which we have, it's both X and W. So what we're getting in GKR eventually is a claim about the multilinear extension, about the concatenation, if you like, of X and W. Turns out that it's easy to break that down into separate claims about the multilinear extension of X and the multilinear extension of W. So the multilinear extension of X, we have X as a verifier, we can compute it by ourselves, but we don't have W. Right? So how do we compute the multilinear evaluation of W, which we got at the bottom? Well, conveniently enough, the prover has already committed to a PCS of W in the beginning. That was alpha. Right? So what we need now is just an evaluation claim about this PCS. Does this make sense so far?
So this is where the diagonalization comes in?
No diagonalization so far. So this is, an honest, this is a protocol that people have proposed, I don't know when, more than 6 years ago, and people are using. There's a startup company or at least one that uses it. This is a nice protocol that people like.
I meant the component where you run a
and what is the component that we're going to attack? You're asking?
No, eventually you want to convince us that GKR has some component that runs a program on itself, no?
You can force it to do something like that. It's not entirely clear where yet in this picture, but I'll show you soon. So just notation-wise, I'll denote this protocol by pi for protocol. And notice that it depends on the PCS that I use, which could be something like fry or whatever you like, and on the depth of the circuit, because GKR, you have these D steps, so it depends on the depth of the circuit. Cool, so that's our nice protocol that we're going to attack. And notice what happens when we apply Fiat-Shamir to this protocol. So first of all, in the beginning, I will need to tell you what Fiat-Shamir hash function I'm planning to use. That is this red H. And then, we proceed in the protocol as before. So I, as an honest prover, evaluate the circuit. I compute the PCS hash of the witness alpha, send them over to the verifier. The next thing in the protocol that happens on the verifier side, do you remember what it is? It was choosing a random point in the multilinear extension of the output layer of the circuit. But now we're doing Fiat-Shamir, we're not choosing stuff at random anymore, right? What do we do instead? So instead of choosing R at random, we hash. What do we hash? Everything we know. Today, we're hysterical. We're not going to have any implementation bugs. Everything we know, we hash. So the description of the circuit C, X, and Y, and the alpha that we got, we hash everything, and we derive R in this way. Okay? Then we start, and the prover also does this similarly. Then we start running the GKR protocol. Notice that GKR was itself an interactive protocol, so it's actually Fiat-Shamir of GKR in this step. So all the arrows are just pointing towards the verifier. And then at the end of this Fiat-Shamir GKR, we're still going to get a claim about the multilinear extension of W, so we'll run the PCS evaluation proof, which again is going to be Fiat-Shamired. And we're doing a proper Fiat-Shamir with all, everything we know being hashed down. Right? So that's a protocol that we get. And I'll denote this by just Fs sub H of the previous protocol. Right? So what happened is just we replaced all randomness whenever we had with evaluations of H. And what we would like for this protocol to be, and we'll show that it isn't, is adaptively sound. So what do I mean by that? What does adaptive soundness mean here? Right, so the first thing that happened is that the verifier chose the PCS parameterization and the hash function H, and then the prover specified a circuit C. In order to violate soundness, I would need, as a cheating prover, to find a circuit C, an input X, an output Y, and the proof pi, so that two things happen. First of all, this is a false statement in the sense that this circuit on input X will never, ever, ever output Y. So if I'm claiming that my circuit C, there exists some witness W so that on given input X will output Y, this statement is false, first of all. Second of all, despite it being false, I can make my verifier accept. So if I give Cx y and this proof pi, which consists of the entire GKR thing and the PCS evaluation, the verifier accepts. If I can do that, I've broken adaptive soundness. Soundness here is adaptive because I'm allowing my choices to depend on the PCS and hash function H. Okay, so that's how we denoted the protocol. As mentioned, this protocol has been widely, I would say, explored in practice in a sequence of works. A bunch of academic papers were studying it and improving it, and also deployed in practice by a protocol called Expander by a company called Polyhedra. So this is from their thing, and this is from their GitHub affix to the attack that we showed, and we'll describe later on what is the fix. Let's first understand the attack, and then we can describe the fix. Okay, but this is very much a real-world attack.
I mean, you do still allow yourself that the circuit C or input X might be contrived in some way, even if the protocol is not.
So we're going to discuss that. I mean, I allow it, but we'll see whether or not that is actually true. But for the moment, let's say we're happy with that. Okay, so I want to state what the result a little bit more precisely is. So the main result is the following. So tell me what PCS you're using, whatever it is, and tell me what depth D GKR you're doing. As long as the depth is sufficiently large, then we show that the protocol is not adaptively sound. What does this mean? Just the contrapositive of what we said before. Given the PCS parameterization and the Fiat-Shamir hash function, we can generate a fully explicit circuit C star, we're going to see it today, and output Y star, so that C star never outputs Y star, and yet we are able to convince the verifier that it does. Okay, so the verifier in the protocol will say, oh yeah, sure, C star does output Y star sometimes.
So sorry, you're saying the circuit depth is going to be a function of the complexity of the hash function of the PCS.
Yes.
So that's where the adaptive.
Yes.
Okay.
And in particular, going to Tim's question, something that naturally comes up when you see this statement, is this our circuit C star contrived? And I would actually say that it isn't. And we'll see in a little bit. At first glance, it might look, but I would argue that it isn't. So we'll try to make that argument. So that's the first attack. Second attack that we do is an extension of the first attack. I call it the backdoor attack. So in the previous attack, we're saying, there's a specific circuit that we're trying to target. But let's say, there's a circuit that you guys are interested in proving. In the second attack, I'm saying the following, actually designing a circuit is hard. So instead of designing a circuit, you're going to go to you're going to outsource it and go to some company, and they're going to give you a circuit implementation. What we're saying in this second statement is that you can take any circuit and change it into a different circuit, which computes the exact same function. So for each and every input in the world, my circuit is going to output the exact same output as your circuit. But for my version of the circuit, I can entirely break security. Okay, so the security here does not depend only on the function being proved, but the actual implementation of the circuit, which is, I think, quite concerning. Yeah, especially, to audit a complex circuit, I described it to someone who does that, and he was very happy, because it would mean a lot of work for him. Third result, we have a version of a non-adaptive attack. I think I'm not doing great on time, so maybe I'll skip that. And I want to just directly show you the main result, which is an explicit circuit for which we can break security. Okay, so not even a high-level idea, just a plan. Our plan is to construct an explicit circuit C star. We're going to be targeting a very specific output string, which is just the vector of two elements, 0, 0. It's a very specific vector, which is convenient. And we're going to build it so, we're going to claim that our circuit C star sometimes output Y star, even though this never ever happens. And it's an adaptive attack, as sort of Tim was pointing out. My circuit C star can depend on the choice of PCS and hash. And the key idea, really, and this is the key idea, we want our circuit internally to try to predict what is the Fiat-Shamir value that's going to be produced. Okay, so let's try to do something like that. So again, I'm describing a circuit C star. It actually won't need any input X. So we're just asking, does this C star, does there is any witness W that will make it output the 0, 0 string? Okay? So let's try to build it. So I have a circuit C star, it just gets an input, a witness W. And it's going to do some stuff, but eventually I want to predict the Fiat-Shamir randomness. And specifically, remember this point R in the multilinear extension of the output that was being computed? I want to try to predict that R. How was that R computed? It was hashing the circuit description, and Y star, which is the claimed output, and alpha, which was the PCS commitment of the witness. Okay? So I want to do something like that. And when I try to do something like that, I run into a sort of a big problem, which is circularity, right? In order to describe my circuit C star, in its description, I need to know its own digest. So how do I do this, right? I need like, only after I finalize my circuit do I know its digest, and only then can I feed it here. So it seemed like a problem. So the way we get around this problem is that rather than hard coding the circuit digest C star inside the circuit, we're going to sort of be expecting to get it as part of our witness. Okay, so let's see what I mean. So this is the actual circuit we're going to use for our attack, C star. So as before, it gets the witness W. The key point is that we're going to interpret W as a circuit digest. And we're sort of going to plan things by expecting it to be our own digest, but we're innocent, we don't know what it is. So we're just treating it as any old circuit digest, even though the attack is geared toward it being our own digest. But for the moment, I want to define the circuit and just saying look at W and interpret it as some circuit digest. Now compute the PCS hash based on W. So compute alpha as you're supposed to. And now we can sort of try to predict the randomness R. I'll denote it here by gamma to distinguish. So what are we hashing? We were supposed to hash our own circuit digest. We're expecting this psi to be that. We feed in Y star, which again was just a 0, 0. And we feed in alpha, which we've just computed. And now we get gamma. We're thinking of gamma as being our sort of guess as to the randomness that's going to be selected. And now I do something a bit mysterious, which we'll understand in a second. I output two field elements, gamma and gamma minus 1. Why? That part is a little bit of a mystery for the moment. We'll see in a second. But this is the circuit for which we're going to be proving a false statement. Is it clear that it's like well-defined, no circularity? Right? It gets W, does this. So first claim that I want to make is that this circuit is never, ever, 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 no matter what W you feed into it, never is it going to output 0, 0. You see why? So it's always outputting consecutive integers. So it's not going to output 0, 0. This is the circuit, never does that. But I'm going to produce a proof that convinces my verifier to believe that it does output 0, 0, even though it doesn't. So we've established claim 1, let's try to prove claim 2. So I wanted to tell you what the prover does, right? So let's rethink in our mind what the protocol looks like. So first thing that happens in the protocol is that the verifier specifies the PCS and the Fiat-Shamir hash function H. And now the prover needs to select what circuit it's using. Well, it's going to be using the C star that I just constructed. That's a circuit that we're going to attack. And then the actual protocol starts, right? So what do we do in the protocol? We need to send, so if there were an input X, we would need to send it. We don't, so we don't need to. We need to send our claimed output, which is Y star. So it'll just be this 0, 0. And we need to send a PCS hash of the witness. So we're just going to do PCS of the digest of C star. At this point, when I describe the prover, I fix the circuit C star. I know what the digest is. I've kind of like pulled the digest outside of C star itself. Okay? The prover still needs to generate a bunch of stuff for the GKR and so on. But let's pause here for a second, because this is where something interesting is going to happen. Cool. So the actual output of the circuit is gamma, gamma minus 1, where we saw how gamma was computed. It was specified a couple of slides ago, right? And now I want to ask you a question. It doesn't depend so much about what gamma itself is for the moment, but what is the multilinear extension of the string gamma, comma, gamma minus 1 at the point R? And because this might be not so clear, I want to spell it out a bit more. So we're looking at sort of a function that at 0 outputs gamma, at 1 outputs gamma minus 1. And it's multilinear, but it's only a single variable function. So it's, again, a single variable function. It's a linear function, because multilinear with one variable is just linear. At 0, it outputs gamma. At 1, it outputs gamma minus 1. Any guesses what it will output at 2? Gamma minus 2. and at 3, gamma minus 3, and at r, gamma minus r, right? But notice, just by construction, when we built our circuit C star, gamma was computed this way. But r, by Fiat-Shamir, how do you compute r? You hash the stuff you saw before. Guess what? It was designed to be exactly the same. So what this means, so we have our, the actual output of the circuit is not 0, 0. But if you evaluate its multilinear extension at the point r, you're going to see a 0. Now let's think about the fake output, right? I'm claiming to you that the circuit output is 0, 0, even though that's false. And now I want to ask you an easier question. What is the multilinear extension of the function that is 0 at 0 and 0 at 1? I'm asking you, what is its value at 2? It's a linear function. It's 0. And at 3, it's 0. And at r, it's 0. Right? So the multilinear extension of both the fake output and the real output is equal to one another at the point r. It's at 0. Okay, so going back, we were saying before that if you take the multilinear extension of two different outputs, because of the distance of the multilinear extension, at a random point, they should disagree. Well, guess what? Our point is no longer random, and they happen to agree. Or we build it up to agree. Right, so what happened really is we started off with a false claim that the circuit is outputting 0, 0. But when, using Fiat-Shamir to choose the random point r, we set it up so even though the claim about the output of the circuit being 0, 0 was false, the claim about the output of the extension of the output of the circuit at the point r being 0, that claim is true. And so we managed to move from a false claim to a true claim. And once the claim is true, we can just run the honest prover strategy. And everyone is happy. So we're actually, for almost the entire protocol, we're just running the honest prover strategy. Okay, so maybe to summarize what the attack looks like. So we have P star, which is the attacking circuit. It gets the PCS description and H. It specifies the circuit C star, our nasty circuit C star. Verifier saves the digest. Then online, our claim is that the circuit outputs 0, 0. And we send a PCS encoding, this should be of C star, sorry, the digest of C star. Now in Fiat-Shamir, we fix R to be this sequence, but now the claim has become true. So the claim that the circuit output there extend at the point R is equal to 0, this claim is true. So from here on, just run GKR honestly and run the PCS evaluation honestly, and the verifier accepts probability 1. So now it goes back to Tim's question that occurs quite frequently, is the circuit C star that we built contrived? And at first glance, you might say it definitely looks weird. It's doing something like evaluating the Fiat-Shamir hash function inside. It's doing a PCS evaluation. No, that's weird. So I want to argue that this is actually not weird in the sense that circuits that we actually care about a lot tend to do these things. And I'll try to give 2 examples. First of all, something that comes up very frequently in these applications is that I give you a particular hash, and I'm claiming that this is a hash of a huge database, say a blockchain or something, that satisfies some properties. So proving stuff for your circuit to depend internally about the hash is very frequent. I would say that that is the typical application even. So that's on one side. The other side, which is I think even, in a sense, even more concerning, something that people, myself included, I guess, tend to do, is to do recursive composition in which you use the proof system to prove the verification process of the proof system itself. And this can be help a lot in different aspects of efficiency. When you do this, by definition, your prover is proving stuff about the Fiat-Shamir hash function. So I would say for the circuit to include the Fiat-Shamir hash function happens all the time. The PCS is maybe not as frequent, but then again, PCSs are often implemented using hash functions. So I would say that I would make the argument that the C star is not at all contrived. And if you do think it's contrived, you can have different opinions, but we do have extensions of the result that do handle sort of like more general setting. In particular, I can take any circuit and insert a backdoor into it so that I can attack it. So far, it's been bad news, and I think to an extent that's going to be the message of today. But there is a question about can we make stuff sound? So one thing I want to point out is that there has been a really rich line of work that I've also been quite involved in of trying to establish Fiat-Shamir security based on standard cryptographic assumptions in the plain model, or at least with a common random string, based on standard assumptions like LWE, DDH, and so on. And I think we've made a lot of progress there. So 2 challenges here. First, even before practicality, all the results that we have so far are only able to deal with a very limited amount of non-determinism. So we don't know how to prove like general NP statements using, forget about practicality. Even theoretically, we don't know how to do it. So in theory land, doing snarks for NP under standard assumptions is an open problem. Probably number 1 open problem in theory land.
So partial is parameterized by the witness length, or what does that mean?
No, so for till like a few years ago, it would have been like no non-determinism. Nowadays, we're able to prove sort of conjunctions of NP statements. So we're proving that multiple NP statements are all correct, and the length of the proof will be proportional to one of them, or a bit more. So you're proving k NP statements, and the proof size is only like, say, 1 or so of them. Yeah.
So there are some works that show like with some special soundness property, like you can remove the Fiat-Shamir, and those papers don't work for.
I'm not sure what line of work you're referring to.
There's like some papers based on lattices and stuff. Are you saying they don't?
So like Brent and David's papers on like
I forgot.
bargs?
I've been to a bunch of talks that show.
Yeah, so they do bargs, so they can do this partial non-determinism.
No, yeah, but not just barg, but also like other papers that get rid of the.
So for snarks for NP, you can do it based on maybe stuff like I/O. You can do it based on knowledge assumptions. That's sort of the extent of what we have.
And what about if you don't need the succinctness?
I mean, if I don't have, I'm not talking about zero knowledge here. So if I don't have succinctness, I don't have anything. I'm only insisting on short proofs. This entire talk is not, you could have zero knowledge on top, but this was all about succinctness. But of course, if you don't insist on succinctness and want zero knowledge, then we have non-interactive zero knowledge, NISC, yeah.
So NISC is like, no, if you don't need succinctness, we don't need Fiat-Shamir.
Right, yeah. I mean, from a practical perspective, we do, but in principle, we don't have to. Yeah.
I think I asked you this in the past, but I thought that CR225 is for all NP.
No, it's for like NC, so much more restricted. Yeah. Oh, so we have a result like a NISC. So if you want zero knowledge but no succinctness, we do have a result for NP.
Oh, okay.
Yeah.
And it's also CR225?
Yeah. So we have two results.
That's why I'm okay.
Yeah. So first of all, it's the limited scope, and second, as Elaine is saying, it is very far from practicality, and in different levels. But for one thing, in contrast to Fiat-Shamir, which only uses lightweight hashing, here it's using very heavy use of public key crypto, in particular things like FHE. So I think it is, rather than saying it's impractical, I would say that it is a grand challenge for us to make it more practical, because a lot of things that nowadays people are implementing 5 or 10 years ago were considered wildly impractical. So I think this is very interesting.
If they rely on Fiat-Shamir, are they using correlation interactable hash functions?
Yes.
I
Yes.
see.
So, most if not all of these works are. Yeah. Okay, so that's sort of like one side. On the flip side, I want to talk about mitigations. Are there ways in which should we just pack up all this amazing work that's been done on the ZKVMs and with Jolt, with SP1 that we're doing at Succinct and others, or how worried should we be about the attack is one way of putting it. I think we should be worried, but I want to point out that actually preventing the attack is quite easy. So in the following sense. So the key source for our attack is the fact that the circuit for which we were proving things could evaluate the hash function. What you could try to do is make sure that the circuit that you're proving for sure is not strong enough to evaluate the hash function, and then I would no longer know how to apply the attack. So for example, what we were suggesting in the paper is to increase the depth of the Fiat-Shamir hash function, for example, by iterating it a couple of times, so that the depth, it's hard to argue that by iterating it, the actual depth formally increases, but practically probably does. You can certainly conjecture that it does. Make the depth of the hash deep enough so that there's no way that the circuit would be able to compute it. And if you do this, I don't know how to run that attack, but I also don't know how to prove security. And sort of like previously we could have said, we have the analysis in the random oracle and we're heuristically instantiating it. And now we can still say that, but we also know that the random oracle does not capture real world attacks that could break actual security. So it really, to me, it really like shakes our confidence in what's going on here. I also want to point out a work that was published just like a few weeks, so a follow-up to our work by Galanon and Elon Yogev, very shortly after our work, so they were proposing a different mitigation. So instead of increasing the depth of the Fiat-Shamir hash, they were proposing to make it sort of like harder to compute the Fiat-Shamir hash drastically. If you make it harder to compute, that makes the verifier slow, so they actually do it via clever use of a proof of work. So that's a nice idea. So it's a different form of mitigation. They also show that their transformation is secure in an idealized model, which is in a sense better than the random oracle model, but on the other hand, it doesn't really capture our attack. So I think the model is natural and it's interesting, but I wouldn't say that, it doesn't like greatly increase my confidence that things are okay. I would say it that way. So just to sort of summarize, what we show in this work is that this random oracle model or idealization it was known for a long time that it's an idealization and it doesn't capture all attacks that you could in principle do. Here we show that it can actually be problematic in practice for a deployed protocol, which I think is concerning. So let me kind of conclude with some open questions that I'm excited about. So as I pointed out, it's not difficult to avoid the attack. You just like increase the depth of your hash function, for example, and the attack will not go through. But beyond the fact that the specific attack doesn't go through, we have very limited evidence for security. So I think studying this is, in my mind, extremely important. So really, especially for students in the crowd, I think this is a fantastic thing to work on and extremely important to this entire like industry of like many billions of dollars. So I think this is extremely important. And as a specific challenge, think of this mitigation. If I make the hash function a little bit deeper than the circuit, can you mount an attack? I would say that this is not a warm-up. I would say if you can do this, then we're in a lot of trouble. If you can do this kind of thing, I would guess that there's nothing like anymore that's specific to GKR that's problematic, and like really the common setting of Fiat-Shamir, say for things like Starks and Fry and so on, would also be in a lot of trouble. Then I think something interesting to do, something we sort of didn't get around to, but I think is really interesting. It seems that the recursion circuit is a candidate for which we could maybe mount our attack. So it would be, then I wouldn't even need to like make any sort of discussion of whether it's like the attacking circuit is natural or not. This would get like a full end-to-end attack on a system. So that I think is really interesting. So think of the system before mitigations were in place. Could you attack it end-to-end? That would be really interesting. I think another super interesting direction is to try to attack specific protocols that are built on GKR, like say Lasso or Log of GKR or other things, in which you don't have a lot of flexibility with the circuit. The circuit is fixed. So it seems you cannot mount this sort of attack. But then again, the evidence for security relies on the random oracle analysis. And so I don't know an attack, and I would love to get either confidence or show an attack. So better confidence than just the random oracle analysis. Lastly, I want to point out that, let's say we live in this kind of nightmare scenario in which Fiat-Shamir is broken and we can't use Fiat-Shamir. And you might ask, are all snarks doomed? And I would say that answer is probably yes. But we do have snark constructions based on other idealized models like the generic group model or something called the AGM, the algebraic group model. And we might say, I tend to think of these as like much worse models than the random oracle model. But the fact that, if we had a break on the random oracle model, it doesn't necessarily mean that those models are kind of broken as well. So I think a really interesting direction would be to try to mount similar style of attack against these other idealized models. And I should point out a work by Dent from 20 years ago. It's a follow-up to this CGH paper that I mentioned, which does give an example of a contrived protocol in the GGM, which is secure as a protocol in the GGM. But if you instantiate the GGM in some way, then you have an attack. Okay, so I think if you're able to extend this further, that would be also extremely interesting. Yeah, Elaine.
What about other proof systems that use random oracle besides GKR?
For Fiat-Shamir, or in what sense?
For Fiat-Shamir, yeah.
Yeah, so our attack really leverages something that is somewhat unique to GKR, which is that you don't commit to the entire computation trace. And that is really the claim to fame, in a sense, of GKR. It allows you to commit to very little information, just a witness. So in traditional proof systems, you usually do the entire computation, commit to everything. And GKR gives you a way to commit to only a small amount. And our attack really leverages it. And for anything more or less except GKR, you are committing to everything, which makes sort of a typically, yeah, and that is, so the thing that gives you efficiency with GKR is also the thing that we attack. And it's something that other protocols don't seem to have. But it's a great open problem.
Two questions. One is maybe more of a comment that maybe it'd be interesting to find out if you agree with or not. So I guess the recursion circuits, they tend to sort of check that a hash is right instead of compute the hash from scratch, if you will.
I don't know. If you think of like a Merkle tree, then you probably got like one side and the other you do compute, right? You got the like one, you have the two children, and one of them you get just to save. You could have given everything, but to save on proof side, maybe you give one, and the other side you compute.
But maybe the way to say it is when you do compute the hash, you tend to get like a bunch of non-deterministic advice to keep. So that kind of automatically keeps the circuit low depth, perhaps lower depth than your standard.
But you know, if you didn't have this attack in mind and you were saying, let's be super aggressive and try to minimize stuff we commit to, maybe our circuit is low depth. Let's use GKR for recursion, right? And I could very well see people wanting to do that, right? So to avoid exactly, for sake of efficiency, avoid committing to the intermediate steps of the hash. Right? So if you didn't have this in mind, I do think there's something you might end up doing.
Yeah, potentially. Okay. Other questions? So I guess trying to give evidence for security of like GKR just for grand products in lookup arguments, say. We sort of know, waving my hands a little, that that's sort of enough to build a whole ZKVM, which is enough for all of NP.
Right.
And then, so we have barriers against. So I guess two questions here. So one
the
is,
barriers are, you mean like gentry-width kind of barriers? Nowadays, I don't know if people would still consider it a barrier. So
okay, so one question is you think people might just manage to show security in the, like snarks in the plain model for all of NP you think that could happen in the
I don't know, it could happen, especially with like people do crazy things with I/O, so maybe. For me, I'm hoping not to be a hater, but I would love to think of attacks. So it seems like very innocent. The circuits you're doing are, say, a grand product, just multiplying a bunch of things. But you're controlling the things so maybe grand product seems more safe, but lookups feel like more general purpose in a sense.
But you can build a lookup argument just out of the grand product. Like once you have a grand product, I can directly reduce lookups to that.
Yeah, but
you're saying that reduction.
The reduction doesn't do much. So I think for both, it's more of a question. So the circuit is fixed. So not too much you can control. The things you can control are sort of the inputs. Yeah. Can you bake in the hash function into the inputs that you're doing and do it? Seems very difficult. I have no idea how to do it, but it seems very important as well. So it's kind of like, do I think it's risky? I think the odds of an attack are very small. If there were an attack, the damage would be crazy. So I think it's very important to invest at least time thinking about this. Yeah.
Can you say some more words on why don't you view gentry-width as a barrier?
So for one, it's been avoided using I/O. So it has a lot of caveats, right? It's only about...
what does it state?
So there's what they're stating is a barrier for proving snargs for NP in the plain model. So when you don't have, say, a random oracle and so on. And what they're saying is that you won't be able to, so suppose you built a snarg and you've tried to, so you have a proof of security. If your proof of security is what's known as a black box reduction, meaning that it would map any adversary into an attack on some like underlying cryptography. So and the way these reductions usually work is, give me an attack, I can use it as a black box to break the crypto. So almost always that's how it works. So that's called the black box reduction. So if you're trying to show that your snarg has adaptive soundness using such a black box reduction, you won't be able to. Okay, so caveats here are it's targeting adaptive soundness, which is, I think in the applied world you do want it, but for the basic notion, non-adaptive might be interesting. And there are tricks that once you have non-adaptive, you can sort of lift it up to adaptive.
How does I/O evade this, essentially?
So I/O evades it because the I/O argument uses a sub-exponential number of hybrids. So sort of, in some sense, sub-exponential assumptions are a way to get around it.
So saying it's an unfalsifiable assumption.
No. It's quantitative. So you need to understand the fine print of Gentry-Wicks, and yeah. And the other thing is, it's true that like usually we like proofs that are in which you use the adversary as a black box, but we do know proof techniques that don't do this. And somehow, to me, the lesson has been with these like barrier results. They're more of like often like indicating in what direction you should try to push.
So this.
So it certainly seems very difficult to do it, but I would say that I would not be shocked if someone managed to do it now.
And then how would you be shocked if someone manages to prove plain model security of like a snark we use today? Because all this I/O stuff is obviously not something we use today.
I would be pretty shocked.
That would be shocking, but the I/O something
a
on
good
I/O.
shock.
Okay.
Yeah. So based on nothing, so just prove period, no like assuming collision resistance, because so we don't actually, an interesting open problem is like does the existence of snarks even imply one-way functions? I think maybe for sufficiently strong snarks it does, so you wouldn't hope for an unconditional thing. But you're probably assuming, you're happy to assume a collision-resistant hash or stuff like that.
Yeah, I mean, look, my worry is that, I don't know, maybe we get snarks in the plain model from I/O, say, but we still have like no idea if, Jolt or SP1, when run non-interactively, is secure, 15 years from now.
Yeah.
That's my worry.
Yeah, so, I mean, this is also true for encryption, right? We don't know that it's secure, but we have candidates and they've stood the test of time for a long time. I would like it for it to be that, so I believe that 15 years from now, both encryption and argument and so on will rely on unproven cryptographic assumptions. The question is, what are the assumptions? I would like them to be sort of as clean as possible, in particular to have the kind of thing that we like in cryptography, which is a win-win. So either, the proof system is secure, or we know how to compute discrete logarithms very efficiently. So I would like to have that kind of flavor. Am I super optimistic about doing that? It seems very, very hard. I would love to do that. I think we're still quite far from there. But 15 years is a long time. So, and we have talented students here, so let's do it.
All right, thanks so much.